Hello, my name is Steve Mann, and I'm presenting here from home. I live with my wife and 2 children upstairs, and downstairs here is my research lab. I'm probably most well known for the invention of the wearable computer. Some of my other inventions include things like HDR, high dynamic range imaging, and also the underwater musical instrument, the hydrophone, the underwater pipe organ, which I invented back in the 1960s and 1970s. There's some examples of hydrophones over there. It was perhaps the world's first human water-machine interface. We have 2 papers accepted in the conference, WaterHCI Part 1, Open Water Monitoring with Real-Time Augmented Reality, and WaterHCI Part 2, Open Water Sensing, Meta-Sensing, and Observing with Drones and Augmented Reality. So now let me present WaterHCI Part 1, Open Water Monitoring with Real-Time Augmented Reality. What we see here on slide 1 is a sequential wave imprinting machine. Let me explain what WaterHCI is. I'm going to do that by way of my iTap eyeglasses. So I'm going to bring you inside my head. I have over here to the left of me a chalkboard horizontally mounted. Water, humans, technology. Where humans and technology come together, we have cyborgs, and there's 2 ways for that to happen. Either the human enters the technology. Manfred Klein said his favorite example of cyborg is a person riding a bicycle. I'd often venture to say that a person on a boat or vessel is also a cyborg, and that puts cyborgs as more than 1 million years old, older than the invention of clothing, older than the invention of the wheel, and even older than Homo sapiens. And in this case, we have a human enters into a vessel, and that's what we call a type 1 cyborg. When the vessel enters the human, this is like with the case with implantable technology. If this is the human here, and this is the vessel or the computer or the technology goes into the human, that's what we call type 2 cyborg, is when the technology enters the human. And the world of humans and water also exists. As Mark Mattson would say, we can swim in the water, we can enter the water, we can drink the water, we can put the water into us. So the water, we go into the water, or the water goes into us, or maybe we go fishing or sunbathing and the 2 are separate. But we understand this intersection quite well already, is the intersection between humans and water. And the intersection between water and technology is also well known. You can have technology in water. It's possible to make technology waterproof and wear it underwater, like these computers can be worn underwater. It's possible also to put the water into technology, like smart plumbing and so on. Or the 2 can be separate, like smart beaches with overhead cameras that monitor and automatically detect drowning. And at the very center, where all 3 of them intersect, in this area here, we've got the waterborg, the aquatic cyborg, and that's kind of what we're looking at is WaterHCI. This is this whole new field that we call WaterHCI, and it's an exciting new field of research. We have a conference on WaterHCI. We're going to have the 24th annual WaterHCI conference on March 30th. 24 years of water, humans, and computers. Okay, now that we know what WaterHCI is, let's move on to slide 3. Slide 3 depicts our outdoor classroom that we built at Ontario Place, the Teach Beach we call it. Slide 4 is just a little bit of fun at the Teach Beach. Sometimes we like to go growler boarding. We do winter swimming almost every day now. Slide 5 is this sequential wave imprinting machine. And this all started in my childhood. When I was about 12 years old, my dad got me this RCA cathode ray oscillograph that someone was throwing out. The problem with it was that the time base wasn't working on it. The dot only went up and down, so being impatient, I put it on a set of rollers. I discovered something quite interesting by accident when I had it connected to this police radar or to an X-band marine radar. What I would see when I moved it is that it would induce this Doppler shift, and it caused the waveform to sit and appear in a set of coordinates in which the speed of light is exactly 0. And I called this extended reality. Then I realized, well, it's only really a one-dimensional graph. So I built this system that has a row of lights on it. The lights light sequentially depending on the voltage present, and then I'd move it back and forth like this the same way. This is a more modern replica of the same thing using LEDs. This is called the sequential wave imprinting machine. SWIM, S-W-I-M. What it's doing is it's picking up the signal from that smartphone. This is a smartphone I built, and it's picking up the signal is being picked up here. The sequential wave imprinting machine is moving here, causing the Doppler shift that's shearing the space-time continuum. So we're in a set of coordinates in which the speed of light is 0. So it doesn't matter how slow or fast I move this. If I move it really, really slowly, the dot goes up and down really, really slowly. And if I move it a little bit faster, the dot goes up and down a little bit faster. And medium speed, the dot goes up at medium speed. And if I move it really fast, the dot goes up and down really fast and creates this plot of this waveform. And if I'm closer to the smartphone, the wave is stronger. And when I get further away from it, the waveform's weaker. If I go through a piece of wood, if I put a piece of wood in front of the smartphone, it makes the waveform weaker. And you can see that my hand almost completely blocks the wave. You can't even see it anymore. So my hand blocks a lot more than the cement, the concrete, and the wood. Why is that? Well, flesh contains water, moisture, and the water stops the radio waves. Slide 6 shows this in a marine context. This is something I built in 1974, perhaps the world's first WaterHCI, water-human computer interface. What I built is I built a little vessel, a little boat, to replace the wheels here to make a simple conveyance to move this back and forth. But my next modification in slide 7, here I now have a sonar instead of a radar, and I've got underwater acoustics. There is a sonar transducer in the water sitting stationary with respect to the trough, and there's a second transducer attached to the vessel. Upon the vessel there's a lock-in amplifier together with this linear array of lights here, and you move that thing back and forth and it gives you this, it swims out the water characteristics. And I was interested in seeing, well, what could we learn about the water? We can certainly measure the speed of sound in water. And how does the propagation of the sound waves in water tell us about the water? Can we learn something about the pollution in the water? In air, it's very simple. Here's my daughter holding a microphone, and there is a swim there with a speaker on the swim moving back and forth on this mechanism. And what you see here is the waveform. This is a metavalence wave function, a photograph of a microphone's capacity to listen. Here's another example. My daughter, when she was 9 years old, made this little thing on a racetrack. She had a race car set with 2 cars, and this little car she built straddles both of the tracks, and it's moving back and forth. Here we see an electromagnetic radio wave. We see the electric field in green and the magnetic field in magenta. Slide 10 is a water-human-computer interface with 2 hydrophones that create an interference pattern and a third hydrophone. Here's another photograph of the interference pattern of these 2 hydrophones with respect to a third one that's moving. The 2 hydrophones on the left of the picture are stationary, and the one on the right is moving through this array. The moving hydrophone is co-located together with an RGB LED, which is showing a complex valued output of the lock-in amplifier on a color wheel. Slide 12 depicts our underwater X-Reality headset, extended reality underwater. Slide 13 shows the sequential wave imprinting machine being towed in the water. Slide 14 shows our smart paddleboard. Here we have a swim, which is plotting a waveform, and we also have the capacity to label the axes using a text generator. Slide 15 shows the sensor pod being towed by a swimmer. And slide 16 shows another example of the water quality measurement within an inner area of the lake. And slide 17 is at another location with the city of Toronto in the background. This is in the Ontario Place West Channel. And you can learn more by looking at the references to our work and other related work in this new field of water-human computer interface. Thank you.